So, apart from the HSLA steels, you look at it here. So, only the Bay-Corning steels would also show the lotus band formation, because the carbon is still in interstitial positions. So, Bay-Corning steel will also show the yield point phenomena, but IF steel do not show yield point phenomena or lotus band formation. That is why the IF steels are very attractive to in those days to make deep drawn components, because the IF steel does not have any carbon in the interstitial position. So, IF steel will show similar behavior, but the strength level will be much lower compared to trip or dual phase steels. Good. So, this table shows about the properties of advanced AHSS steels comparing with HSLA steels, and if you look at it here, the mechanical properties are varying from say 300 MPa until to 700, even up to 1000 MPa. Okay. Whereas in HSLA steels, it is very difficult to change the mechanical properties, because the microstructure is more or less fixed and the alloying elements are fixed. But in DP and especially in DP and complex phase steels, you can play around with the volume fraction of phases, the amount of martensite or any other phase apart from martensite, for example bainite present in complex phase steels. We change around, play around. The strength level can be changed from 300 to even up to 1000 MPa. So, third generation dual phase steels, and we add alloying elements and precipitates to get the strength levels even up to 1 gigapascal at DP 1000, for example. So, therefore, the DP dual phase steels and complex phase steels, in some extent trip steels, are very attractive, because we can generate the steels with varying properties with reasonable ductility. If you look at it here, for example, the HSLA steels, the yield strength of 350 MPa and 450 UTS, the elongation is about 25%. Whereas in a DP steels with a similar strength level provide slightly higher even elongation than the HSLA steels, and by increasing strength, of course, you reduce the elongation, but still it is acceptable. For example, DP 500, DP 600 with 20% elongation, and it still is very handy to make components out of it. And trip steel, and we have reasonable yield strength, and the ductility is very high compared to the similar strength containing DP steels, because of the microstructure consisting of retained austenite. Okay, so we will see what is the role of retained austenite trip steel, and as of now we can understand that the trip steel possesses much higher uniform elongation, total elongation, than the DP steels for a given strength level. And apart from that, we also have a martensitic steels, and this is mainly the hot forming steels. The hot forming steels, you do not need to worry about the elongation, because this elongation is actually after forming, but before forming these steels contain a simple ferritic pelletic conventional microstructure. So, you can form it easily, and then upon forming you quench it to get a martensitic microstructure. So, we can achieve the strength of 1200 to 1500 MPa at the component level. Okay. Good. So, we will now look at in detail about the physical metallurgy of these the advanced AHSS steels, mainly dual phase, trip and hot forming martensitic steels. So, as already explained, dual phase steels, these steels containing two phases, mainly the ferrite and martensite. Okay, so here you see the matrix here. So, these grains are the ferrite grains, and in between the ferrites, and you also see the grains of martensite, right. And we generate this multi-phase microstructure or two-phase microstructure by a special heat treatment. Okay, and this special heat treatment makes sure that we have martensite in formation in reasonable cooling rate, and when the martensite forms during this treatment, during this heat treatment, and martensite also when martensite forms in adjoining ferrite matrix, there is significant amount of volume expansion, which can lead to the formation of large amount of mobile dislocations at the interface between the ferrite and the martensite. and in order to accommodate the volume expansion of the martensite formation. And these mobile dislocations that are present at the interface between the ferrite and martensite increases the ductility significantly, because you all know that the plastic deformation is actually caused by the moment of dislocations. If you have a large amount of mobile dislocations, and these dislocations can enhance the ductility of the material significantly. So we also know that martensite is in a high strength phase. When you have martensite, strength also increases significantly. So by having the martensite embedded on a ferrite matrix and with the large amount of mobile dislocations at the ferrite and martensite interface, and we can get the combination of strength and ductility. Right? And how we get this microstructure, we will see the thermal cycles what we use to get the microstructure in subsequent slides. Before that, we will see the microstructures of other steels, for example trip steel. Again, trip steel also, as I explained, has a very good strength as well as ductility which is slightly higher than even dual phase steels, and because of this microstructure I show you now in this slide. The trip steel microstructure typically contains the ferrite and the bainite and some amount of austenite. Okay, so this austenite is known as retained austenite. Generally, you all know that austenite is high temperature phase in an iron carbon system, but by doing some tricks, tricks meaning by adding certain alloying elements as well as carrying out some special heat treatments, we can stabilize retained austenite at room temperature among the ferrite and bainitic microstructure. Okay, so you see that in this microstructure there are three colors of phases, the matrix. So these guys are ferrite, and this brown guy over here, so this is actually bainite, and the bright blue islands you saw over here, these are all retained austenite in the microstructure. Okay, so again this bainite what you see over here in this microstructure, it is not conventional bainite. Basically what you over here is the bainite without cementite in between the lots of ferrite. So you recall when I talked about the bainite formation, the bainite contains a ferrite lot, in between you have cementite, and then again ferrite, and then cementite, and then again ferrite and cementite in a conventional bainite microstructure. But again in this trip steel, we add some alloying elements which can suppress this cementite formation. So you may end up forming ferrite with slightly supersaturated in carbon concentration, so carbon atoms. And by doing so, we gain some advantage of carbon migration to the austenite that is transforming, and because of that we can stabilize retained austenite at room temperature. I will explain in a thermal mechanical cycle of the trip steel heat treatment, wherein we can understand how the microstructure can be generated in a special heat treatment. The advantage of this microstructure is the enhanced ductility coming from the transmission of austenite to martensite upon applying a load. Okay, so this transmission of austenite to martensite upon load is actually known as a stress induced transmission. And so when you make a component out of the steel, you can also deform it because of the retained austenite. When it actually transforms to austenite, so transforms to martensite by stress, the mechanical energy you put it in is consumed by this transmission, resulting in increased elongation during forming. And apart from that, because the austenite is transforming to martensite during forming or during deformation, and we also gain advantage in terms of crash performance. So how? Suppose if you make a component out of trip steel and you have a retained austenite in the microstructure, and if automotive is actually subjected to a crash load, the austenite transforms to martensite during this deformation, and but thereby absorbing the load. The material becomes stronger during this crash because of the formation of martensite from austenite. So we gain advantage in terms of formability because when the austenite transforms to martensite by load, the mechanical energy coming from the deformation load is absorbed to transform the austenite to martensite. Thereby we increase the elongation significantly. And apart from that, by leaving retained austenite in the formed component, and this retained austenite can transform to martensite while applying crash load. So the component becomes stronger during applications. So, this microstructure of ferrite and bainite without cementite and the retained austenites is very attractive for automotive applications because of the strength which is achieved from the alloying elements as well as the presence of bainite and the supersaturated bainite and the elongation, superior elongation given by the stress induced transmission of austenite to martensite. Okay. And the third generation, the third significant improvement in terms of strength we achieved in automotive steels is by martensitic microstructure. So in this process of forming martensitic microstructure, we won't significantly change the alloying elements compared to say for example DP and trip steel, and hot stamping steels or martensitic steels, they have a similar alloying element except some special alloying elements which increase the hardenability significantly. So one of the alloying elements is boron. So we add some amount of boron. The microstructure to begin with, it's still a ferritic palladic microstructure, what you see over here. And this ferritic palladic microstructure containing a slight amount of boron is taken to high temperatures to form austenite, to completely transform the ferritic pallade into austenite microstructure, and then we form the component at high temperatures, and then subsequently we cool the components after forming to form martensitic microstructure. Okay. And during this cooling process, we already seen from CCD diagrams, if hardenability is significantly higher and even with slow cooling rates, we may end up forming martensite, complete martensitic microstructure upon forming. So the components gain a significant amount of strength because of the formation of martensite. The strength level can go up to say 1200 to 1600 megapascal upon forming, but the forming is easy because the material flow much easily at austenitic temperatures. So you form whatever components, shapes in deep drawing and forming, and then subsequently cool to get a complete martensitic microstructure. And during this process, we increase the strength, and also we overcome problems during forming such as spring back, so which is also minimized during this process. So these three steels, dual phase steels, trip steels and hot stamping steels, they are all now commercially used, and we look at in detail about the actual forming, the microstructural formation mechanisms, as well as in subsequent classes we will see the welding behavior of dual phase strip and hot stamping steels while making the auto components. Okay. To summarize the physical metallurgy of these first and second generation and the third generation advanced AHSS steels, the steel product development is actually driven by the emission norms plus the improved crash performance required to meet the various standards. So the need for high strength steels with acceptable ductility arise because of these emission norms and lightweighting. The microstructure of conventional steels used in automotive industries are very simple ferritic or ferritic palladic, but they were not sufficient to give high strength required to reduce the weight to down gauge the thicknesses of materials used in that. So we looked at the microstructures of conventional steels like IF steels, Baconic steels, HSLA, ferritic palladic, carbon manganese steels, and why these steels cannot be used to achieve lightweighting, because once you increase the strength in these steels by adding alloying elements or heat treatments, and the ductility comes down decrease significantly. So we went ahead and developed some of the advanced ISN steels such as dual phase steels, trip steels, and complex phase steels. So we looked at the comparison between mechanical properties, comparison between mechanical properties of DP steel and trip steels. Why with given yield strength, DP and trip provides much more superior elongation, total elongation, as well as high UTS. That this combination of strength and ductility is achieved by the multi-phase microstructures in trip steel and the ferritic martensitic microstructure and dual phase steels. Okay. So we also looked at the microstructures of dual phase and trip and hot forming steels. So what are the phases that are present in these steels? So with that, we will conclude this physical metallurgy chapter, and we will move on to the actual heat treatment that are used to generate these complex microstructures of dual phase strip steels, and we will also look at the simple the basic thermomechanical cycle used in hot forming operations to achieve the martensitic microstructures in subsequent lectures. So I will start with introduction about the heat treatment that is commonly used to generate dual phase and trip steel microstructures. Okay. So before going to that, as I already explained, apart from the carbon, which is generally added in the iron system to form the microstructures and to achieve the strength and various properties, and these steels also contain manganese, silicon, aluminum, and some amount of phosphorus, which is actually considered detrimental for mechanical properties and weldabilities, but we add slightly low amount of phosphorus as well for various purposes. So these alloying elements are added to achieve certain goals. For example, manganese is added to get significant solid solution strengthening, and silicon and aluminum, they are added especially in trip steels to enhance the formation or retention of austenite at room temperature. I will discuss it in detail when we look at the thermomechanical cycles for trip steel heat treatment. And the phosphorus is also added because it is very effective solid solution strengthener. Okay, so this graph shows the normal thermal cycle that is used to produce dual phase as well as trip steel microstructure. Okay. So in a first we look at the dual phase thermal cycle. So in a dual phase steel thermal cycles, so we take the microstructure, this could be even ferritic palladic microstructure, to a temperature where we have a two-phase equilibrium exist. For example, now we do not take it in conventional heat treatment. If you look at the phase diagram, recall the phase diagram I taught you in the first classes. So you have a phase diagram showing the reductoid region. Okay, so we have a austenite and we have a ferrite plus austenite and ferrite, and then here ferrite plus cementite. So in a conventional heat treatment like annealing, normalizing, you must have heard, the material is taken to a fully austenitic region, right, and then subsequently you can cool it to various cooling rates to get the microstructures of ferrite perlite or whatever, the martensite, even if you quench it faster based on the CSTT diagrams. Whereas in the dual phase or trip steel heat treatment, we will not take it to a fully austenitic region. So we will take the material to a temperature where we have a two-phase microstructure exist. So in this case, we will take it to temperature regions where we have both ferrite and austenite coexist in this microstructure. The advantage is I will explain now. So, we take the material to a temperature, for example here, say in this case I mentioned about 759 degrees centigrade, that is where conventional DP steel, and if you have say 0.2 weight% carbon, and we will take it to a temperature say 800 degrees centigrade, and we hold it there to form a microstructure with a mixture of ferrite and austenite. Okay. So, what happens here, as already explained, when you hold it here, this line gives the carbon in austenite line, and this line gives the carbon in ferrite line. So, by keeping in these two regions, if you have a bulk concentration of 0.2 weight%, the austenite which is actually forming while during this holding at this temperature, say for example 800 degrees centigrade, will get enriched because of the carbon partition, carbon migration from the ferrite that is coexisting with austenite. So, your austenite that is forming at this temperature would have a much higher carbon concentration than the bulk carbon concentration. So, by doing so, by enriching the austenite that is actually present in the in this holding at 800 degrees centigrade, will have a much higher carbon concentration of than the bulk carbon concentration. The advantages over here is, we all know that the hardenability increases significantly by increasing carbon concentration. Okay, so, now by holding a two-phase microstructure region, and we enrich the austenite in carbon given by the your A3 line, this line, and because of this enrichment, now if you cool it to room temperature, the microstructure containing both ferrite and austenite, and this austenite would easily transform to martensite. So, you have a microstructure, okay, you have a two-phase microstructure. Okay, so, you have austenite over here, for example austenite here, and these two austenites are now enriched in carbon compared to the ferrite, and ferrite carbon concentration is much lower compared to the austenite. So, now this austenite, because of the increase in carbon concentration, when you cool it, even at reasonable cooling rate, this austenite can transform to martensite, right. So, that is how we form the martensite slightly easier than in a conventional heat treatment, where in conventional heat treatment, if you go to the complete austenitic region, your entire austenite would have a bulk carbon concentration of 0.2, whereas in here, because of this the partition of carbon between the ferrite and austenite, we enrich the austenite in carbon, and thereby we increase the hardenability of the austenite significantly. So, when you subsequently cool to room temperature, we transform the austenite into martensite, okay, and the cooling rate is again dictated by your process, and if you have a high carbon concentration, even with a slightly significantly lower cooling rate than the austenite contain only 0.2 weight%, you can achieve the martensitic transformation of this austenite. Now, this austenite transform to martensite. This transformation also accompanied by the volume expansion in the lattice. So, if you have a volume expansion, so what will happen then, this austenite when it transforms to martensite, okay, so you will also have expansion driven dislocation formation at the interface between the austenite and the ferrite, right, because the volume expansion should be accommodated, right. So, this accommodation is actually done by the forming a large amount of mobile dislocations at the interface between ferrite and austenite. So, we have two advantages. When austenite forms to martensite, we increase the strength, and because of the volume expansion, we also increase the number of the density of mobile dislocations that are present at the interfaces to accommodate the volume expansion. So, now because of this the special heat treatment, where we take it to intercritical region and then we quench it or cool it to room temperature. So, the austenite which is present in the intercritical region transforms to martensite, and thereby the strength increases, as well as because of the volume expansion accommodation, we also generate a large amount of mobile dislocations, which can give us increased ductility. Okay. So, with this we will conclude, and then we will come back again, we will look at the trip heat treatment and what are the roles of these alloying elements and forming the multiphase microstructures. Okay. Thank you.